fortunate today to have Professor Neil Lawrence. So he's the DeepMind Professor for Machine Learning at Cambridge. Spent a lot of his career at Sheffield, and I guess many of us know him from the podcast Talking Machines, which if you don't know, you should. It's really good. So as part of the introduction, I'd just like to highlight a couple of pieces of good citizenry that he's involved in and that I'm personally very inspired by. So the first of these is the Data Science Africa initiative. Perhaps you could say a few things about that at some point, but the important thing is that it's going to Africa and training people there to do the data science as part of their training programs there, and just kind of really improving the overall quality of data science that can be applied to real-world problems there. So the second thing is the Open Data Science Initiative, and I guess there's two things that I picked up that I just knew about from that. And so the first of these is the Neurips experiment, which we discussed whether this talk should be about the Neurips experiment. It's very fun. Obviously we chose not to talk about that, and we're going to hear it instead about Gaussian processes, but kind of everyone should know about this because it's one of the biggest data examples of like how peer review works, and the conclusions from that was that it's good for identifying poor papers and poor for identifying good papers. I think we could probably all relate to that experience. And the other thing that I think is very important is about open access publishing. So that's so Neil's involved in the proceedings of the Machine Learning Research Journal. Is that even the right word?
Yeah, proceedings. I don't know. Yeah.
So this is a gathering of the proceedings of all the major AI conferences, and they're free to publish in, and they're free to read, which is a rather rare combination, and the Journal for Machine Learning Research is trying to grow this ideology, and I think that more of our community should push behind that, because I think it's very important. Anyway, so with that, I'd just like to welcome you. Thank you so much for coming, and I'm very much looking forward to the talk.
Thanks, Daniel. I guess the common thing with those is I kind of like building communities. I don't know, because I think that when you're in a community, I suppose people outside science think it's all about individuals. I think it's all about communities and connecting people and sharing information. And it also feels like important that we control our communities. So Data Science Africa, I helped found it, but I'm actually not involved in the running of it at all. It's all run by African data scientists. I go out there and talk and give patronage, but the whole point is to empower people to run their own communities, to do the things, giving them the tools they need. And PMLR in some sense is just the same thing for worldwide communities around data science, a free published journal. But yeah, so today it's we're going to talk about deep Gaussian processes, which is I suppose the technical piece of work that I guess a lot of my career was kind of leading up to how you could do something like this, yeah, it's going back to from I think about 2001 when I would see Jeff Hinton talking about deep learning. But I'm going to try and give you a sort of motivation. I'm not going to go super technical in this talk, but I'm just going to give you a sort of introduction to the motivation to why I think these models are interesting and how they fit in a broader context of what's going on in machine learning model, and then say a little bit at the end about some of the interesting developments I've seen in this area. One of the things I learned quite early on in research, primarily because I was trying to recreate a model someone else had created and build on it. I was trying to extend it. I was interested in the model. And then I found that they'd written this paper called Extensions of that model. I won't say which model it was, which listed everything you might possibly imagine you could do with this original model, which is a Bayesian extension, doing mixtures, all the things you might do with a probabilistic model. And basically, I think that killed all the research in that model because it gave no one an in to try and come and build on that piece of work. And that's kind of what you want. To get into something, you want a way of playing with it. And one of the things I'm sort of almost actively doing at the moment is enjoying the fact that other people have picked up deep Gaussian processes and are extending them and doing interesting things with them. I do work on them, but I sort of really like the community that's around that. So the context of this sort of whole deep learning work, I think so people keep talking about this fourth industrial revolution. The thing I love about the fourth industrial revolution is the first of the industrial revolutions that was named before it happened. It's sort of a thing that economists say. And I think it's so interesting if you live in Britain. I mean, in Sheffield, where I used to spend a lot, there's nothing industrial in Cambridge. The Industrial Museum is an old sewage works. But, there's a lot of industrial stuff in Sheffield. And you see steelworks, you see the evidence of coal. If you go to Glasgow, you see shipbuilding. I mean, these things have an enormous effect, actual industrial revolution. But it's sort of, I guess that context makes you think a lot about what machine learning is. And when I'm in a maths department, so I have to be very sensitive because the techniques we use in machine learning are no different, really, from the techniques people use in statistics or other branches of maths. So I kind of think that machine learning is really about a philosophy about how to combine these things. And we could say, of course, statistics could be this, or a lot of applied mathematics is this. Right? If we go back to Gauss and his prediction of series, then what Gauss had was a model based on Kepler's laws and some data. And he combined the two with compute. And of course, in Gauss's day, the compute, he wrote an entire book about it. I think it took him 2 months to make a prediction of Ceres' orbit, given the data he had, to make a prediction, which was a year after the planet was lost, about where this planet would emerge from behind the sun and could be recaptured. They called it planet at the time. It's, of course, a dwarf planet now. And at the time, I don't think there was any differentiation. People say that's the origin of statistics, but you could argue that's the origin of applied maths. You could also argue it's the origin of machine learning. So I think that the interesting thing about this sort of little equation here is where the emphasis is. Because in machine learning, a lot of the emphasis has been on the quality of the prediction and less emphasis on the interpretability of this system. So you differentiate that with statistics. Statistics classically is sort of saying, well, I'm actually trying to understand whether there's any meaning in the data, right? And the reason I use a model is as a tool in classical statistics. I'm typically trying to use as little modeling as possible to draw a conclusion from the data, so I'm allowing the data to speak. Whereas in machine learning, since you're not trying to draw that conclusion, you're not necessarily trying to find out something about the data, you're just trying to make a prediction. And I think that these things, obviously they're connected. I once joked that in statistics, you're sort of trying to remove human subjectivity from data. Whereas oddly in machine learning, we're trying to introduce human subjectivity to data because we know that the subjective things we do allow us to make predictions about objects. We can be fooled. So they're sort of like, so in other words, statistics are trying to almost turn humans into computers, and machine learning is trying to turn computers into humans. And neither of us can do this, but we end up meeting somewhere in the middle using a lot of very similar techniques. The difference is often the motivations for why we're doing it. So this equation would be similar, but some of the choices that a machine learning person might make when they're combining things end up being different. So data, I kind of think everything is data. So it has this origin, I think, in Laplace. It's actually donné, as in givens, and that's the Latin. Everything we're given. So I like thinking of data as anything that's actively or passively acquired or whatever. Of course, in statistics, classically, we're looking normally at surveillance data. But in machine learning, okay, people are aware of that, but they wanted to look at observational data. And I think that even this sort of phenomenon we're getting now is people are just acquiring data, without any. If you go back to the origins of statistics, a lot of it's about the design because data was expensive to collect. But if you look at machine learning, it evolves in a world where data is just being collected with no purpose. I call this happenstance data because I think it's really difficult data to deal with, and it's a sort of major challenge across the field that we face at the moment. So the model, and we can think of models in different ways. I actually tend to think personally of models as broadly split into two categories, weakly mechanistic and strongly mechanistic. So strongly mechanistic, I mean I've got some differential equation and I actually believe in it. So I'm thinking like, I've got Newton's laws, or I'm doing what Gauss was doing, and I think of that strongly mechanistic. But all other models actually in some sense have some weak mechanism form inside there, so they typically assume smoothness or something like that. You know, you would all be surprised if I disappeared from the left-hand side of this room and reappeared at the right-hand side. You wouldn't be surprised if you were watching on Zoom, but in real life, we expect things to be smooth. And this is emergent from properties that are underlying everything that are mechanistic, diffusion equations or whatever else. And they just happen a lot, that sort of the maths washes out in some way. So I think of that as weakly mechanistic because it's still a mechanistic assumption. And I think one of the things that has interested people in machine learning is that we're actually encoding beliefs about the regularities of the universe. And some people call that inductive bias. Of course, it is a form of bias, but it can help us make predictions. And that's where I see the philosophy of, and of course I've been in the field 25 years, and I'm the first to admit that when your conference has gone from 600 people to 16,000 people, your opinions about what your field is don't matter anymore because you're being outvoted by the 15,400 people who think it's something else. So I'm giving you the view I've had that may have shifted because most people in machine learning have not been in machine learning for 25 years. And then the prediction, I mean, it could be an action, a quality score, it could be regressing out of value, it could be a categorization, it could be anything. So it's a very sort of broad way of looking at things. And then if we go to a combination of these things, I think there's two fundamental parts. Not all machine learning algorithms have these parts. You can think of like things like k-nearest neighbors that don't actually have a prediction function. But generally speaking, a lot of the time we're trying to solve this with two things. A prediction function that is actually encoding beliefs about the regularity, so often it has something like smoothness, or we might choose it to be linear because we might think things are linear. And an objective function that measures the mismatch between that, the sort of predictions coming out and the data that we're seeing. So of course in Gauss's case he had some basis function based thing where he had sines and cosines involved, and then he actually was using, well, of course that's the least squares priority dispute, so he modeled it as a Gaussian distribution, which he didn't call a Gaussian distribution, which he credited to Laplace, because Laplace developed it for the Laplace approximation, and then that leads to least squares. So this has been going on for sort of a very, very long time. So what's new? Well, I think first of all, when I think about this, what is going on in the broad picture, is all we're doing is we're trying to automate processes by codifying them and automating them, right? So I think that when you look at the effect of machine learning on society, why are you trying to get that prediction? Because there's certain things that humans can do, like recognize objects. I mean, I don't watch Spring Watch is on now, and they've now got AI in Spring Watch. I don't know if you know Spring Watch. I don't watch it every. Well, I think it's quite cute, but I don't really watch it. But you know, they monitor animals in some area and say, oh look, the bunnies are coming out of their burrow. And they've got all these remote cameras, and these remote cameras now have AI in them, meaning that they are detecting when the animal's coming out, what the type of animal is, what the sex of the animal is. And I think if you go back, I mean, not 10 years ago, it was clear that it was starting to happen 10 years ago. 11 years ago, no one would have believed that we were close to doing that. And then 10 years ago, people were like, oh, that will be possible. So if we compare, I kind of like this view. I spend a lot of time, and my community spent a lot of time, the early machine learning community, assimilating and understanding how statistics looked at things. My supervisor, Chris Bishop, he wrote a book called Pattern Recognition and Neural Networks, which really brings a statistical perspective, back in 1996, a statistical perspective to how we were looking at these machine learning models. And then he wrote a follow-up, Pattern Recognition and Machine Learning, I think in 2006, that did the same. And actually most of my community started to assimilate that actually the sort of thing that was going on was that we were modeling things in something like this way, more close to a classic statistical way, where this is an additive model, where we might think, and I'm thinking like, what's the probability, like, so I worked for Amazon for 3 years to see how these things were being deployed in practice. And if you were at Amazon, you wanted to know, well, what's the probability someone's going to buy a jumper, a woolen jumper? You might make that probability, you might think that's dependent on how old they are, start to feel the cold as you get older, and how far north they are. And so you might develop some equation, some linear equation, and compute the log odds so in some form to allow you to make that type of prediction. And what I think is really interesting when statisticians would write down this model, they would always use beta as the parameters. And I take that, so I also do that because sometimes I try and do statistics. If I write down beta as the parameters, it means I care about the value of the parameters because I'm looking to use these to make some interpretation about what's going on. So I'm carefully building my experiment and controlling for the right type of inputs in such a way that these betas are meaningful because they give me some sort of sense of what's going on in terms of why people buy jumpers. And at Amazon, actually, you saw this happening a lot. So econometricians do something called bridging. So when the automated systems would make a decision, they would actually fit linear models across the operating point of this decision to try and understand what they would call the variance, which I think I would call the residual, what the residual was due to. So why the prediction in terms of what stock we ordered in was mismatching to the actual stock we got, and you're trying to explain that. And you end up going for sort of a linear model like this to explain that. And you see people reinventing that in machine learning now, and it's called MIME or something, where they're going in to complex models and linearizing in order to explain what's going on, which is so interesting because, of course, what that's effectively showing is that you can't get away with what machine learning people try to do, which is to entirely focus on the prediction. At some point, someone wants an explanation. So what you're starting to see now is an enormous amount of statistics being bolted on the back of machine learning as they try and explain what these models are doing. Whereas if you approached it with a classical statistical mindset, you would ensure your model was explainable from the start. So I think most of that is familiar. So we ended up with this sort of problem that, I mean, I'm actually personally much more sympathetic to this type of stuff. Oddly, you know, I started out doing this, but I think the more you work on problems, the more you want these tools to answer questions. Like if you're looking in the African context and you're looking at the sort of things people are doing, you're not, yes, you can make use of these new machine learning techniques to do something interesting like a collaborator out there, or colleague I should say, counts whitefly on the bottom of cassava leaves automatically with a mobile phone. But at some point, that's just an input to a system where that system's going to go to the Ministry of Agriculture in Kampala and make a statement about how widespread cassava disease is in the country, and they're going to have to make a decision about what interventions they should be making. So even though that counting thing may not be that interpretable, when you start doing disease modeling and changing policy, you still get back to this need for interpretability. So in terms of how that panned out, this is my example of face recognition of what goes on in these models, and you know, many of you will probably have studied them. Like, this is a Callisto block art detector from Facebook in 2014. Well, it detects any face, but what it did was, it's the first face recognition system that could perform as well as humans on cropped versions of the face. So if you gave humans a cropped version of the face only, and you compared it to what the machine was doing, and you know, in terms of the experiment on a controlled data set, not video cameras in the wild, they were able to perform as well as humans with this model. And this is kind of the things people have been building. So here in this case, and you wouldn't do this anymore, but in this case, they actually did some work geometrically to put a mesh across the face, so you can use sort of geometric understanding of images to do that, and remove the rotation of the face before you put it into the model. So that's what that's signifying. Nowadays you wouldn't do that, you would just put the image directly into a neural network. And then you've got the RGB colors of this thing, and then you start putting them into these convolution layers, these little feature detectors. And the key point about these, I mean, these are very like, they are sort of little convolution filters, but the parameters of the filters are learned, and they're learned by observing enormous amounts of data. And to get to the sort of scale where they can do this, this is what I think is the important thing, is when I started machine learning in the 1996, these models already existed, right? And people tried them on digit recognition. What we didn't have was the scale of data that these models could really refine the input features in this way that it's doing here to get the level of recognition we need. And the big breakthrough in 2012 was the ImageNet data set, which was 14 million images labeled up. And every time you see one of these breakthroughs, it's typically 30 million games of Go or something like this is being used in order to train these things. And every time you look at it, you realize no human could ever see that amount of data in their entire lives. You know, and yet they can perform on these things. So something's happening quite different from what humans do. But these are highly parameterized, and I think of them as just basis function models, where basis functions are feeding basis functions, are feeding basis functions, are feeding basis functions. Okay? So, and that's been the case for a long time, since going back to the 1960s, people were proposing, Rosenblatt was proposing this type of architecture. It was just, what's happened is, in the 1980s, people sort of proposed gradient descent on it, and then in 2012, we got data sets that were large enough where this started working. It's a bit more complex than that, of course, and lots of people have different architectures now. But the key point here is like 120 million parameters, which, back in the day, everyone would have got very upset about how underdetermined those parameters are. And they are massively underdetermined. And there's lots of really cool, interesting work about how these models are generalizing, why they're generalizing, that I'm not going to talk so much about today. But the way I think of, when I'm describing these models publicly, I talk about pinball. So this is an old classical French pinball machine, I think from the 18th century. And what I basically sort of say is, look, a data point, if it was a one-dimensional data point, so if we had one color of one pixel from Callisto-Flockhart, then the data point starts at the top of the pinball machine like this, and it goes through layers where those layers are parameterized. Here I've shown the parameters as a set of location of pins. And you're composing those layers together. So it's a composite function of these different layers. So in this case, this wasn't Callisto-Flockhart, and it's accidentally gone into the yes box, so that's an error. And then when we go into, that was Callisto-Flockhart correctly classified, and that one's not. So the notion I think of is that this is what you're doing when you're training these models. You're moving those basis functions around, and these basis functions, they are these sort of unusual flat things that then go straight off linearly, often, very often. And once you move those basis functions around, you do it in such a way that your data point falls through the system correctly. Now, I think even in this case, you get the sense that in order to do this, you must have to put quite a lot of balls through the system to ensure that all your examples of Callisto-Flockhart and not are being correctly classified. But I can't remember the dimensionality of those images, but the dimensionality of those images means that actually that input space at the top, instead of being one-dimensional, like if it's a 1,000 by 1,000 image, then it's a million dimensional plus 3 dimensions RGB, it's 3 million dimensional. So you're playing this game in 3 million dimensions. So you're putting these balls through this system. To me, that's kind of what helps me think, oh, these things must be really data hungry. That's why you require 14 million data points to put through to start getting reasonable results out. Because the number of possible paths through this 3 million dimension, of course there's throttling on it, so the dimensionality is changing as you go through, but you get a sense of what's going on. There's going to be sets of parameters there that are untouched by data, presumably. Right? And you could start perhaps looking for them and taking them out. Very, very alien to not just, I think, what the classical statistics community would have thought, but we had absorbed all those lessons by 2012, what the machine learning community would have thought, because classic generalization, we would have said, what you're doing, we can't do stuff like this. I'm not going to talk a lot about, I think there are really interesting papers that explain what's going on there, fascinating stuff. But what I'm going to sort of do instead of that is say, well, what this has always made me think about. So I draw my neural networks upside down. So these are the inputs, and then these are the basis functions, these ReLU units that people use in each layer. And this is just a fully connected, it's not a convolutional neural network. So what's going on, though, is I would write it in this, I would use phi, because I started to learn about statistical notation. And I'm using W for my parameters because, as I said before, if I use beta, that means I care about parameters. Here, the parameters are a means to an end, a means to a prediction. I don't really think they're meaningful themselves. And what's happening is that I just take an x, it goes through one basis function model where the basis set is phi, and the phi happens to be these flat followed by these linear portions, these rectified linear units, and then it does the same thing until I get an output. And that's kind of the mathematics of what's going on in this little pinball system. So when I look at that, it becomes much clearer that this is just a sort of composition of these basis functions. But this is incredibly powerful. So if you look at, so my chair is funded by DeepMind. It's odd to be funded by a company that 10 years ago was a minor collaborator on a rejected EPSRC grant we submitted. So, oh, that's cool that you think deep learning is going to work. Could you join this EPSRC grant to give us some industrial capability? And of course, they've grown massively. And one of the things they did is solve these AI problems that allow the computer to go. But they're just using these techniques when they're doing that. I mean, they've got lots of advances, AlphaZero and all this stuff. But at this time, I think they started with 30. I get confused about the numbers now. But there's like 30 million games of Go going on here. It's either the number of, it observed every game that had been stored in human history. This version, AlphaZero didn't. They just had to play against itself. And used these sort of neural networks to do, to sort of evaluate the quality of a given board as part of the movement. And techniques known as reinforcement learning that are basically allow you to sort of look at the end of the game and propagate through time, different errors, and things like Monte Carlo game tree search. All sorts of techniques that you can pull together in order to make this amazing thing happen. But the thing I love about this story, you know, and I met Dennis, we were doing a Royal Society thing together on machine learning at the time, and we saw him when he was shortly before the game took place. And Van Hui, who was the European champion that they defeated, had been employed by DeepMind, and he was busy playing AlphaGo to try and find things that AlphaGo didn't know about. So imagine that sort of pinball machine, the area, trying to find a place in that pinball machine where a ball had never been before, right? Because if you can put the computer in that place, all bets are off. It's not seen any data there, it hasn't done any training in that region. You can't say anything about what it's going to do. And they knew that was a possibility. Dennis said, well, that's a possibility, and that's what we're trying to work away from now. And I think the most impressive thing about the whole escapade is that Lisa Doll won a game. And he won a game because he found exactly one of those points. So in that, I call these points where data's never been a Sidolian void. Because I think it's such an amazing sort of thing that he achieved to play the computer into this totally unfamiliar territory and force the computer to do something stupid. Now, what I think fascinates me about that is, so yeah, in machine learning we do like to think about how humans behave. If humans are put into unfamiliar circumstances, they actually react in all sorts of interesting ways. They start hesitating or withdrawing, they reduce their sort of, you know, they have confidence, right? They have a notion of doubt that creeps in. And these models have sort of a notion of doubt. And one of the things that I've sort of spent my career, or my whole career even after I started, is worrying about doubt. Now this is important. You can see these slides online and the stories here, and I think I link also to the NTSB report. But this is the first self-driving car to kill a pedestrian. And it's an Uber self-driving car. It has 3 sensors on it. It had a video sensor, it had a radar sensor, and it has a LiDAR sensor that I think you can just about see on the top there. And what happened in this circumstance is that the pedestrian walked across the road outside a crosswalk with a bicycle walking in this way. And since the car didn't have a sense of the notion of a pedestrian with a bicycle walking in that direction, and the pedestrian wasn't in a crosswalk, what happened is, if you read the NTSB report, the pedestrian was easily visibly sighted. That's also in the report. If the driver, the safety driver, wasn't paying attention, they were watching the American version of The Voice, I think. And there was plenty enough time for them to say, you know, the lady was, she should have heard the car, but she didn't hear the car. She's a homeless lady. She's going across quite a long road. You can see it all on Google Maps. And what happened is the car spots her. It keeps changing the categorization of what this entity is. It thinks it's a blockage in the road, like a car stopped. It thinks it's various different things, none of which it is, because they fall outside the context of what the model's being trained on. It hasn't seen these sort of things. But rather than sort of go, oh my goodness, this is an unfamiliar situation, we should slow down, the car only applied the brake sort of half a second before impact. All the Volvo's impact prevention systems have been switched off to stop them intervening, and they would have stopped the accident. And I think the shocking thing about it is the speed at which the impact occurs, because the brakes applied so late. You can actually see that with all these sort of accidents. When you look at the ones where people have autopilot on, you see the same thing. The interesting thing about them is that the speed of the car, because it doesn't recognize the situation and it fails, it doesn't brake at all, which is so different from what a human would do. In unfamiliar circumstances, if we saw something we would actually tend to sort of reduce the energy in the system, I think, as, because that's a sort of sensible, safe thing to do. So the lack of this sort of doubt in these systems has pretty strong consequences. So there's various ways uncertainty can arise. Uncertainty arises from scarcity of training data. So even 14 million isn't really enough because these all can play into different regimes. Mismatch between the set of prediction functions we're choosing and all possible prediction functions. And uncertainties in the objective. I really think that's so interesting, uncertainties in the objective. Almost all machine learning is contingent on the idea that we understand the objective. And that's true of actually most things that we design, not just machine learning, operations research, mathematical things. We believe we know what the objective is. Yet it's very unclear in the real world, to me, what the right objective should be. So, how do we deal with this? Well, I'm really interested in Gaussian processes, and this is my sort of 3-slide introduction to Gaussian processes. So a Gaussian process gives me, instead of a deterministic way of creating functions, I have a stochastic process. And what I like to think of the stochastic, this is a set of slides that Nicola Durand, who was a postdoc with me, put together, and I liked it, so I've stolen it. So basically what you have is a way of generating functions. So this is all Bayesian inferences like this, really. You just got a way of generating something, and a way of generating a lot of them. So, and then what you do is that represents your beliefs about the universe, the way you think the universe's functions exist. You combine them with data, and you throw away all functions that are inconsistent with your belief about the universe. I love Phil David's frequential work, which I think is also very similar and it's non-Bayesian, but I really like this perspective of things. And the beautiful thing about Gaussian process is in most Bayesian modeling, that process is analytically intractable. In fact, there's these really cool methods called ABC that try and do exactly this, and then have some sense of mismatch between the samples from your simulation and your data. But they're quite compute intensive. But in a Gaussian process, it turns out you can do this analytically, which is really, really nice. So you get this analytic ability to come up with what we call the posterior distribution, and now you're seeing samples from the posterior distribution. Okay, so how does that relate to this model, what we're showing here? Well, it turns out that each of these systems can almost be seen as a Gaussian process. So what I do is this. So inside each of these, the thing that everyone used to worry about is these things overfit. Now it turns out, this is the way I viewed this back in about 2012 or something. That you've got all these parameters and you're going to overfit. So the way I was viewing it at the time is that the proposed solution, they had all these weird things called dropout. You take out some of the parameters at some points and whatever else. But here's an alternative solution. So these W's, which would be B's in statistics, what we're going to do is reparameterize them. So we're going to use a singular value decomposition, but it's not actually going to be a singular value decomposition because we're not going to bother constraining these things to have to be built from normal vectors. All it is, the key point is what we're going to do, singular value decomposition like, in that it's just going to be of this form. In fact, we're even going to absorb the lambda into U and V. So we effectively have a low-rank version of W. Now, in neural network computer science parlance, what you call those is linear units. So you can expand, if you do this, you can think of this as a U and this as a V matrix, these sort of connections here, and these as a set of linear basis functions, right? So you're sort of bottlenecking at each layer. And that turns out to be really interesting because, and there's a lot of work on this now, but I think the intuition for me on this is very clear. I haven't looked at the sort of technical proofs. But one of the things we know is that if you have just one layer one of these, so if we just take this thing here and we expand that number of basis functions to infinity, then because of central limit theorem, the output here will be a Gaussian process. As long as when we select weights, we have some constraints on the variance of those weights. The output here will be a Gaussian process. So for one of these layers, the larger I make this, the closer I start getting to this output being a Gaussian process. Okay? Which is one of the, if I'm sampling these weights in some way rather than fitting them, which is the sort of thing that I want to do. Now, actually, if I don't just increase the width of this layer, but if I increase the width of that layer above it simultaneously, then the whole thing turns into a Gaussian process. So if I don't have this bottleneck, if I just increase the width of these layers, then central limit theorem will also tell me, oh, you're just doing a weird Gaussian process covariance function. And people are starting to say that now. Oh, look, I've got these infinitely wide neural networks. And they turn out to be Gaussian processes. But I, with this model, was specifically trying to get away from Gaussian processes. Turns out this bottlenecking is very important in that. It allows you to build models that are non-Gaussian processes. Because Gaussian processes have weaknesses in that they have properties that don't allow, for example, jumps in them. I think I've got a slide on that in a moment. But what we're doing with this model now is just rewriting it in this form. So we've got these intermediate variables I call Z. And then the key point is now, once I've got these intermediate variables Z, I can write it in a form like this. And now I can note that from this point, so this is the input going through a matrix V, going through to Z1, which is then fed into a basis function set being multiplied by U1. And that H1 is then going through the same thing again. So this is a repeated pattern here. Now each of those repeated patterns, if I increase these basis function sets to infinite number of basis functions, turns out to be a Gaussian process. So rather than, it's a cascade of these sort of neural networks, which then I think of in this form. So throwing away, when we're doing it with a Gaussian process, we've taken the number of basis functions to infinity, and you end up with something that looks, instead of having those h's everywhere, you just have the z's. So this is what I call a deep Gaussian process. But I think there's something else that's interesting about it, is, and before, I gave a talk in Warwick in probably 2012, 13 or something like that, and definitely at that time I would refer to this as stochastic process composition. Because what I think is really interesting about what's going on here, and it's a little bit different to the motivation for deep neural networks. What you're doing is you're starting with a stochastic process that's a Gaussian process, and by composing it, you're changing the class of process that you are creating to a non-Gaussian process. And that, for me, was very important, because it's not just about, in classic deep neural networks, it's about these little filters and extracting these filters. Here, it's about changing the nature of the uncertainty representation you can do. I'm going to spend a little bit of time talking about that. So, of course, for a sort of, if we look at this mathematically, we've not done anything here, because a composite function is just a function. But why it's interesting is because it's composed from these simple parts, a little bit like that deep neural network thing was with all those filters in it for Callista-Flockhart's space. But in this case, we're composing stochastic processes together. So the input to one stochastic process is the output of another stochastic process. And that will change the nature of the process. And also, of course, make everything intractable. Okay, so key point is it's also composite multivariate. So in each layer here, and you actually have control of the dimensionalities of these Fs. Like the thing I was saying before, and I appreciate I'm throwing a lot of intuitions at you and not giving you any rigor, but that's because I'm a computer scientist. What I was saying before is that if the dimensionality of these Fs is also allowed to go to infinity, then this whole thing is just going to be a Gaussian process. So the non-Gaussianity comes from making sure that these things are finite. And that turns out to be a sort of key parameter of the model. In fact, one of the things that we have done briefly is try to assess that by these infinite binary processes that Garamani and Griffiths came up with. But yeah, it's only a small paper. I don't think we gave it a full treatment. What's also really cool about this is it's equivalent to a Markov chain, right? So actually you're seeing that this deep model is just a Markov chain, because each of these is just, so this is a P of Y given F5, P of F5 given F4, P of F4 given F3. Each of these is a Gaussian process. So that's just another way of writing down the same thing that sort of goes off the page. That's X then. And that's nice because there's certain analytic things you can do in Markov chains. So there's a paper, or I can't remember, Mark Dunlop, Andrew Stewart, Mark Geronimo, I'm probably missing an author, where they analyze deep Gaussian processes. And they say, this isn't what you would do in practice. They sketch over this, but I still love the paper. in practice, you wouldn't make these all the same Gaussian process typically, but if you do, then you can analyze this and look at the stationary distribution of this thing. And so you can sort of say, well, how many of these Gaussian processes do I need to compose together before I hit the stationary distribution? Because it's a Markov chain. So I can start talking about this, what that's converging towards. And what it converges towards is not Gaussian. In practice, we often compose it from each of these entities being a different type of Gaussian process, which makes that analysis hard. So, yeah, just drawing that in a certain way. And I think I've sort of motivated that. Oh, so I suppose these key points, it's a beautiful property of a Gaussian process that the derivatives of Gaussian processes are also Gaussian, and we can use that in all sorts of nice ways if we have derivative observations. Very elegant, we get a joint Gaussian process over the derivative observations and the process itself. But it also implies that a Gaussian process will not model jumps very well, because if you've got a jump process, clearly its derivatives occasionally, they're very, very heavy-tailed. Now there's another nice work by David Duvenot, I think Zubin's on there and others. I'm not so keen on the title, but the work's really nice, where what they show is when you compose these Gaussian processes together, that under certain parameterizations, the tail of your derivative distribution gets heavier, right? So instead of having a Gaussian tails on your derivative distribution, which is necessarily implied by a Gaussian process, what you actually get is heavier tail derivative distribution. And I'll sort of show a little example. I'm going to just show toy examples. People are using, we use these, we actually use these in multi-fidelity modeling to help design the Amazon drone that does fly but isn't commercialized. And I know other people have been using the multi-fidelity modeling. Lots of cool applications in the real world, but I'm not really going to talk about them today, just for time. So I think this stochastic process composition is like a new way of constructing more complex processes based on simpler components. And okay, so it makes everything intractable, and I'm not going to talk much about the way that we deal with those intractabilities, but it often gives you ways of sampling from them or something, because you know that within the graph you've got something that is tractable as a subcomponent. So we use variational methods. It also allows you to do things like this. I'm always so interested in the notion about what if I had medical data and at one level I got some really fine-grained information, something like coming out of a scan or something like that, high-dimensional phenotype information. And at another level I have something which is much coarser-grained, like survival. How do I build models that try and stitch these things together? And for me it feels that the challenge is you're working at different levels of granularity. And one of the things that can be emergent from these models, and is actually Jeff Hinton's original motivation for doing this type of thing, is the idea that at the top you're at a coarser level of granularity and at the bottom you're at a finer level of granularity. And I really like that idea. So I sort of just draw that here. You can start, of course, building trees. You can build any graph you want out of sets of Gaussian processes, and I think that's a very rich and interesting thing to do. So this is Andreas who did the sort of original work. So I used to say at the beginning of talks, the universe isn't as Gaussian as it might like to be. And then I found out by talking to Carl Kramer that there was a time when the universe was probably Gaussian as far as we can measure. So this is the cosmic microwave background. And at that moment of condensation, what you're observing is a spherical Gaussian process. So, and the parameters of that Gaussian process, and I always try to remember this correctly in case there's a cosmologist in the room, there are 6 parameters of the covariance function of that Gaussian process. And those 6 parameters are the fundamental parameters of our universe. How much dark energy, how much mass, I don't know whatever the 6 things are. And that, the covariance function you're seeing is a single sample from that process. And cosmologists find that interesting because our Earth is a nonlinear function in some way, where the nonlinear function is all the condensations that have happened of that initialization. And one way you can think of the deep Gaussian process is it's starting with the Gaussian process at the input level, and it's putting that through other Gaussian processes which themselves are nonlinear functions. So it's kind of, not that this F itself would be a Gaussian process, but it's my joke that what we observe today is the result of the deep Gaussian process. There's some links there to, I think, modern reviews of these things, and some links to software. But the thing I really want to show you is just a little bit of intuitional results. So this is a data set, marathon data set that I like to use, partially because, as Daniel mentioned, it comes from when I We're the first Data Science Africa. We did it in Uganda, and it was just after Stephen Kiprotich won the London Marathon. And there's nothing like giving people data sets that are close to something they're interested in to increase their interest. So it's originally inspired by data in Rogers and Geronomy, but it's the paces for the marathons at the Olympics across, this is the first Olympics in, I guess that's Athens or something, isn't it? And it's got this interesting outlier, which is because when the Olympics was in St. Louis, so I don't know if anyone here is a marathon runner, but you know, like, I think that's almost achievable for me, that one. The reason it's, so everyone got lost because they had cars for the first time, and they kicked up a load of dust, and it was a mess, and only 4 people finished. So it wouldn't have been achievable for me in 1904. So you've got this outlier where everyone got lost from here. And then other than that, you've got sort of interesting effects, like they don't run marathons across wars. So you get these gaps, and you know, you can hallucinate, is the pace of improvement getting better or worse? There's another really cool thing that Alan Turing was a marathon runner. Does anyone know what his marathon time was? 2 hours 45, which I think he ran that in 46, and I'm going to put him about here. He was 10th in the national championships for running marathons in 1946, which is extraordinary, isn't it? 2 hours 45 is a very fast marathon today. And then, of course, it's got quicker. So if we fit a regular Gaussian process to this, Gaussian processes have all these things, like they have Gaussian noise. So there we go, that's the thing on Alan Turing, 2 hours 46 minutes 3 seconds. And he's, I think you can just see here, I think he's 10th if you count it down. Extraordinary. So we can ask questions, what's the probability Turing would have won an Olympics if it had been run that year? But then if we do a standard Gaussian process fit, this is what we get. We get, because there's an outlier, the noise variance overall is too large, and yeah, not great, is it? I mean, you can deal with this, you could try and do things like introduce likelihood functions that have heavy tails, and that kind of works. But here's trying to do, what happens if you do a deep Gaussian process here? Well, this is the result of doing a deep Gaussian process fit, with just 2 layers. So one Gaussian process, it's like the pinball, but it's one-dimensional in this case, so it's just like the pinball. All the examples I'm going to show are just like pinball. There's the sort of year coming in the top, and the pace is coming out the bottom. And this is the bit. So immediately you see that it actually can capture heteroscedasticity. It's sort of, it believes in higher variance at the beginning and lower variance at the end. It's not doing, it's a very powerful model. It can do all sorts of complex things, but it doesn't seem to be overfitting. And if we look at samples from the model, I don't know if you can see those, because of course I'm showing you error bars that are at 2 standard deviations, but these aren't Gaussian error bars. There's not a Gaussian system. So my error bars are sometimes quite misrepresented. You can see there's quite a few points up here, there's quite a few points up here. So we are seeing more samples than we might expect outside the error bars. But there's this sort of samples, and those samples are effectively ball drops through this system. But in this case, our pins are like uncertain in their location. They move around, so the ball itself becomes a distribution. So this is the first sort of layer of pin stuff. So as you can see, it's broadly linear, but with some quite large variance. And notice it's flattening at the end. Right? So it can construct that type of uncertainty by starting with that thing. And they only have some very sort of, you know, the flattening is not marked, but of course it's sufficient to map all these years onto the same point. So when you look at the next layer, and what was that point? That point was, I mean, this is the latent variable, right? So it's not necessarily interpretable. So 3.5 or something like that. And then we're coming in that latent variable, all those points are being mapped to here, you can see it, right? And they're going all to the same time. So it's sort of, it's saying, well, the rate of improvement is stopped in that first layer, and that's why you're starting to get as well, in these earlier layers, notice this is quite high confidence, apart from where there's no data, as the Gaussian process will often do. But because there's high variance on the input here, that high variance on the input is high variance here, which is then pushed through this curve, and then is large variance on the output, which is what gives us the overall curve. Now, because I started with pinball, here's my visualization of what's going on in the pinball machine. So because it's actually, the colours aren't great, apologies, but actually what it's trying to show is that you've got a diffusion for these balls going through. So it's like, that as you go down, you're going through some Gauss-Markov process. By the time you arrive here with some variance, and then you get map forward. Now, notice the monotonicity of this diagram is not quite monotonic because it's splitting over there, is why the line, if this was pure linear, it would just be straight parallel lines. Yeah? So to give you a sense of how to interpret what's going on in this diagram. I'm just going to do a couple of other examples which have different characteristics. So step functions, very, very hard for Gaussian processes to model. And that's what happens if you fit a standard Gaussian process to such data. So this is a step function with a deep GP. Now here, you have to be very careful about interpreting these error bars, because I'm going to have sample from this system. And look where the samples end up. They end up, what you're seeing is the variance associated with a highly bimodal distribution. Because what it believes is, it believes in the possibility of transitions at any point once it's left the data. Here, I mean, actually I forced it, put overlap on the step, so it's harder than the step, right? So here in this region here, it's sort of thinking it's going up and down quite a lot. And that means it's sort of also happy with the idea that it would go up and down a lot in these regions here. Still weaknesses in this model, it hasn't, you know, it doesn't fix everything. But, and that one is built by composing several GPs together. So here's the first layer, second layer, third layer, fourth layer, and you can see how the points are mapping. So how's it building this? It's almost just constructing, it's composing 4 sigmoids together to make a step. Yeah? And you actually do have, in order to, because the original process is, remember I said as it goes deeper, you get heavier tails on the derivative distribution, you do have to compose several together to get that sort of thing. And I really like the pinball plot, because it looks like a space invader or something. So, what, you know, unless you're in the, coming in the middle there, then you tend to bifurcate down one of 2 sides by the time you get to the end. And that's how, so the input there is saying, well, that bifurcation occurs there, but, you know, because of the uncertainty, it's very high at these levels, you can start from that side and end up across here as well. So that's how it's ended up modeling it. It's all about how the uncertainty pushes through, which is very different to what's going on, I think, with a lot of the deep learning models. This motorcycle helmet data is a helmet being tested by being accelerated into an object. So what you, sorry, not accelerated into an object, it's going with a constant speed. The acceleration is 0, then hits an object. So you see here, 0 acceleration. And then, of course, it has a very strong negative acceleration, but it sort of flies back forward again. So you get this sort of chirp effect. Okay, that's the Gaussian process fit. There's this heteroscedasticity again in the noise. And again, just using a 2-layer deep GP, you capture some of that heteroscedasticity. And how has it done that? Well, broadly similar to the Olympic data. So the chirp is very clean, but it's injecting noise into a roughly linear thing that's feeding the chirp. And that's what gives you the interesting things around here. Again, the error bars are not very helpful because nothing's going on up here actually. It's very flat because this curve is coming from wiggling that chirp left and right. So it's very light-tailed above it actually in terms of the distribution, but it's skewed down here. So it's highly skewed in this region here as a result of that. Okay. So I'm going to stop there because I want to make sure there's time for questions. But the last thing I would have talked about is work by someone else called Vincent Dutour, who was actually looking at, who has sort of discovered that if you look at a certain type of covariance function, which is a very cool covariance function, you can actually interpret deep neural networks as deep Gaussian processes. And what he proposed in this paper is using a deep neural network that's been trained on large amounts of data to initialize a deep Gaussian process and then get the benefits of very, very large data which you get out of deep neural networks and the propagation of uncertainty through. And I think that that's a sort of very interesting approach, so I just wanted to mention that. But then I'll stop there to make sure that we've got a little bit of time for questions. It's a very cool piece of work because it recognizes that these ReLU covariance functions can be seen, they're non-stationary, but they can be seen as the result of the projection of a stationary covariance function on the sphere, so like Schrodinger's equation type stuff, being projected onto the real line, which is a very, very cool thing. And they use that result to sort of create their variational approximation, which looks like a deep neural network. And there's a few of their results there. So, thank you very much. The conclusion is basically, yes, deep learning is doing all sorts of powerful things, but to me the most interesting thing that is missing from a lot of the literature is what happens when you push uncertainty through these systems, because I really like stochastic processes. And I'm arguing that actually this is approach in general. You can compose together stochastic processes to get new types of uncertainty. And it might be possible for things that are not Gaussian processes. Thank you very much.
Thank you very much. That was fascinating. Right, questions from the audience? Do I get to start? Excellent. So let's try and figure out whether your example from the car crash, right, is your kind of thesis that if we were to, for example, be able to say what is the probability that there is a person walking in front of us, that these methods can address that, and if that claim is true, what's the barrier to those models already being in these systems?
I think it's a great question, because I think it's much more complex than anything we've done so far, because I think a lot of the hesitancy we have is emerging from uncertainty about the right objective function. And I don't think you see a lot of work on uncertainty about it. You see multi-objective function work. I did play once with what happens if you try and introduce weighted objective functions, put uncertainty on the weights. That's something you can try and do. But I kind of feel that there's a big gap there. It's certainly the case, and we pull back from that. It is certainly the case that if you look at, so anyone here work with stochastic control? So hesitancy is something that is emergent in stochastic control. So in stochastic systems, when it's sort of emergent if you are trying to achieve a target, that sometimes the right action is no action. Because sometimes, and that's with a defined goal, because sometimes it's like, well, because it's stochastic, I could just do nothing and things could work out for the best, right? In deterministic, that's not likely to happen. You can see that's not going to happen. So you get these effects of delayed action emerging in stochastic optimal control, and I think that's interesting because delayed action is clearly what you want in the presence of this uncertainty, but I don't think it necessarily fixes this overall. I think that it's something that humans are extremely good at, is the sort of hesitancy. Statisticians are extremely good at skepticism, not diving in, being trained to not jump to conclusions. And machines, certainly the way we're building these systems now, which is composing these deterministic models, aren't good at it. So for that reason, I think stochastic is interesting. But I agree, I don't think that the things I've said give us the final solution.
Because there is there are alternate systems in which hesitancy is a really bad idea, right? So, for example, if you're a prey animal being chased.
But it's interesting how often prey animals hesitate. Yeah. So, rabbit in the headlights, right? So it's true, and actually that is exploited. But it's so interesting also deer. I mean, there are lots of examples of prey animals hesitating, even though it does seem like a really good idea. Bad idea. Yeah. So it's absolutely true. We can definitely find examples where it's a stupid thing to do. But yeah, it's clear that even in that case, animals will do it. Yeah.
Right. Does anyone? Hey.
Thanks for that interesting talk. I noticed at some point in your slides you seem to be putting down a low rank assumption on the weight matrices.
Yeah.
But then I didn't sort of see that it kind of came in later. Was that just?
Yeah, it just enables me to see what's going on here. I mean, and I suppose I say a lot of this is in the papers, but I think a lot of this is just in my talks. But it's when you're sort of turning these deep neural networks into deep Gaussian processes, and I totally agree. I wasn't clear on it. At this point here, it's not clear where your Gaussian process appears, because it's true that if I increase the width of this layer, something Gaussian process-like should be happening, but it's happening here, and this is directly into a basis function. So what happens if I increase the width of both of these layers, which is what I want to do, because I want this layer to be a Gaussian process as well. Central limit theorem effects mean that I get a Gaussian process with a covariance function, which is the composition of whatever the covariance functions of these basis function sets were as they feed together. So in order to avoid that happening, I don't want to take the limit of both these sets of basis functions going wide. I'm sorry, I know I'm assuming a lot of contextual knowledge around GPs. And the way one does that is by introducing a fixed. So if this is K2 and this is K1 in dimensionality, if I take K1 and K2 to infinite limit, then I still get a Gaussian, and all the other Ks, I get a Gaussian process. But if I introduce a Q in the middle here, if Q is greater than K1 and K2, the model's the same, but if Q is less than the smallest of K1 or K2, I've got this sort of bottleneck thing going on, and that's what that low rank thing is. And then I can see that the Gaussian process is the point at which I can probe the system and find that something should be a Gaussian process is now there. And that means I can take that limit and that limit, but still end up with something non-Gaussian overall. So was that...
Yeah, no, that was really helpful.
No clearer than
no, it wasn't.
First time through.
Much clearer.
Yeah. Any more questions?
So my supervisors are working on sort of stuff similar to this. He's sort of working on, like, if you take a deep Gaussian process, then you take those layers to infinite width.
Yeah.
And then basically he shows that if you just do that on like the intermediate layers, then sort of law of large numbers says that everything just sort of builds sort of expectation, you get a really boring model.
Yeah.
But then the sort of weird thing he does is he then takes the outputs to be infinitely wide as well. I was wondering, have you ever sort of been reading about stuff like that or heard about things like that?
Yeah, I have to say, I mean, I'm not a good mathematician. I'm very intuitive about things. When I think about infinite, so if I think about a regular Gaussian process, and I think about the output going infinity, and what do I would mean by that I'm going to assume that I'm sampling that process independently for each output, and scaling down the dimensionality, scaling down everything with the dimensionality as it increases. So the statistics between those points end up being something very interesting. And then, because I don't understand, because I don't understand Hilbert spaces, but I noticed that somehow the statistics of this space look similar to the sort of things that go on in a Hilbert space, because now the expectation of, so if my covariance function is kx x prime in that space, then the expectation of y and y prime in that space is given by that, minus the mean, you see, mu prime, is given by the covariance directly, precisely, because everything concentrates in that high dimensional expectation. The integrals all concentrate. The higher dimension, and that's actually why everything stays Gaussian. Because if I'm going through, if I'm starting at an input and I'm going in here to a high dimensional space, then the statistics in this high dimensional space concentrate, even if because the functions are independent. And so when I go into the next space, I'm actually putting in a point process into this thing. I'm not putting in something with variance into it. And that's the intuition about why you have to do this. Because if this layer was infinite itself, those statistics would concentrate around the covariance function of this first layer. And the mean would also concentrate as well. And so you wouldn't be pushing uncertainty through to the next layer, and everything would come out as Gaussian. But having said that, I don't understand necessarily why who's your supervisor, by the way?
Lawrence Aitchison.
Ah, right, yeah. Okay. So I haven't seen the work, and I'd be interested to find out more about how that comes out. I did. When the first thing you said was it equivalent to making this infinite depth?
Infinite width. So basically, at each layer of the deep Gaussian process, if you have like one Gaussian process, there's like 5D outputs.
Oh, this one goes infinite. Yeah, so that's what I think is the... Yeah, so then you end up with something, I think it's a Gaussian process with a convolved kernel.
Possibly.
Like a composed kernel. Yeah, so that's the thing I was trying to avoid by doing this.
Yeah.
I think that there's this, so, and I may be wrong because I don't, you know, I'm sort of, as I say, an intuitive mathematician. So there's this paper by Cho and Saul called Deep, I think, Kernels or something. And I think that effectively what's going on in that paper is what happens if you do that as well. That there may be subtleties about how these things are being built that mean that that's not true. But that, when I was doing this work, that was kind of my feeling about that, and that's why I didn't go in that direction, because I wasn't sure why. That's an interesting paper, but I wasn't sure why you would want that in practice, because I was interested in a non-Gaussian system.
Yeah, I think sort of his motivation for it is like, if you just take those bits to infinity, then yeah, everything collapses again.
Yeah.
You sort of lose representation on it.
Actually,
If you, yeah, sorry.
go ahead, sorry, yeah.
I was just going to say, so then if you take the output to infinity, then it's sort of like, he shows this thing like if you look at the sort of normalized joint distribution, it kind of balances the prior and the likelihood together again.
Oh, so, right. Oh, that would be interesting. You should send me a link. The other thing I'm quite interested in is if you do both. So you have, so I sometimes think of these, as I implied earlier, as a sort of, you know, ideally I would want these to be sampled from the IDP. So you could have a countably finite number of these sampled from an infinite distribution like the IDP. I kind of think that's cool. And then behind that, that could be added to the uncountably infinite that would come from a model a bit like the one you described. And I've not done that at all, but I sometimes conceptually think that's interesting.
Yeah. Okay, yes, we're running over time. All right, so thank you so much again. That was a wonderful talk. We've got you here for a few more minutes if anyone's got any burning questions. And you're at the JGI showcase tomorrow. So if anyone's, there's loads of great things going on tomorrow, so do check that out. The other thing is we've got the last seminar in this series next Monday. That's Nick Whiteley talking about spectral representations and manifolds, how they emerge in that. That's going to be a great talk. So let's come on to that too.
Right.
So
Thank you very much, Daniel. Thank you very much for the invite and apologies for
video.